Okay, so this video is about successive ionization energies. Okay, so if you remember, ionization energy is the energy required to remove one electron from the outermost shell of an element. Now, successive ionization energies would refer to the ionization energies of electrons removed after the first electron is removed. So the first ionization energy is denoted I1, would refer to the first electron being removed. The second ionization energy, denoted I2, would refer to the second electron being removed. Third ionization energy, I3, would be the third electron removed, and so on and so forth. Successive ionization energies are always greater than the ones before. Okay? And so if you were to look that up, it would tell you that it's greater because there's less electrons, which would make a more positive atom based on the Coulombic charges of the positive positive protons in the nucleus. But I do want to bring up something else that affects the ionization energies and those charges, and that is the repulsion that similar charged particles have on each other. Okay, so because electrons are always negative, they're going to repel each other. Okay, so there should actually also be some repulsion going on between these two valence electrons as well. And so since there's repulsion between all these electrons going on, they want to have as much room as possible from each other, so they kind of shimmy away from the attraction of the nucleus. Well, if this electron is gone, then we don't have this repulsion between these electrons. So there can actually be this tighter attraction between the nucleus and the electron that's left. So it holds it just a little bit tighter, which means we're going to need more energy to get rid of the second electron. What you might see a lot is a chart that looks like this with IE, or again, you might see just the I with the subscript of the number referring to which ionization energy. So the IE is just ionization energy. First ionization energy would be 799 kilojoules per mole. The second one is obviously greater. That second electron is being held tighter by the more positive, now charged ion, 2,420. The third one is 3,660. And then the fourth one, notice what happens from the third ionization energy to the fourth ionization energy. We have this huge jump from just under 4,000 to over 20,000 kilojoules. Okay, so when this happens, what we assume or what we know will happen is that these first three electrons were all valence shell electrons. 1, 2, and 3. Now this fourth electron, where we have this huge increase in ionization energy, is now in a different shell, closer to the nucleus, so it's going to have a much greater attraction between the nucleus and the valence, the new valence shell. So there's a much greater force of attraction between those two particles. Therefore, we have much greater ionization energy. Okay, so whenever you see a jump like this, such a large difference, then that's when a valence shell has been emptied, and so now we have a new valence shell closer to the nucleus, which has much stronger attractive forces between the nucleus and the new valence shell, so it would require much higher ionization energies to get rid of those electrons. And what they'll do a lot is they'll ask questions about, well, what element could this be? And so they might give you a hint like, it's in the second period, which means, well, it's in the second period. We have 1, 2, 3 valence electrons, so we know it's going to be boron. Or they'll give you a multiple choice question, and you'll just look for the element that would have 3 valence electrons.